Hello everyone, my name is Jiajun Dang. I'll represent my co-authors to present our work. From multi-view to Hollow-3D. Hallucinated Hollow-3D RCNN for 3D object detection. Let me first give a brief introduction to the background. Point clouds are a set of points to represent 3D objects in scenes. Each point in the point clouds at least includes 3 channels to indicate the 3D position. Sometimes there are also other attributes, such as reflection intensity, RGB values and timestamps. As an emerging data modal with precise distance sensing, LiDAR point clouds have been placed great expectations on 3D scene understanding. In this paper, we focus on 3D object detection for autonomous driving scenario. Given a set of point clouds, 3D object detection aims to localize and categorize objects in a predefined range. Although with precise position information, point clouds data are notorious for their sparsity and unstructured storage. These two properties make it challenging to perform feature representation learning on point clouds, while the real-world applications raise the demands of both accuracy and efficiency on the algorithms. The previous works can be categorized into 2 directions according to whether projecting points into 2D planes for feature extraction or extract features in 3D space. The former series start with projecting 3D points into regular grids in either bird-eye view or perspective view, and then exploit 2D CNNs for detection. For example, the most representative work, Point Pillars, groups points as pillars in bird-eye view, and extracts the pillar feature with a simplified point net module to construct a pseudo-image. LaserNet are similar to point pillars, but use the inherent perspective view representation. Since this kind of method only rely on 2D CNNs for feature extraction, they are relatively efficient. The other series extract 3D contextual features in 3D space. Since the point clouds are sparse and unordered, feature extraction with the raw points should be conducted with advanced point-based operators. The pioneer work Point RCNN introduces a 3D region proposal network based on PointNet++, and devises point cloud RoI pooling to extract RoI features for box refinement. Another solution to extract features in 3D space is to discretize the points into 3D voxels, and leverage 3D convolutional networks. The pipeline of voxel RCNN is similar to point RCNN. But the whole pipeline are built on voxels. It capitalizes on voxel RoI pooling to take advantage of good locality property of voxels to accelerate the RoI feature extraction. Then, let's see the motivation of this paper. As we mentioned before, it is a valid problem to highlight both the accuracy and efficiency when designing a 3D object detector. For previous methods with projected views, the over-squeezed information in each single view usually leads to unsatisfied performance on distinguishing and localizing objects in 3D space. For methods that extract features in 3D space, the runtime latency of 3D feature extraction is much higher than operating on 2D representations. And both the advanced point operators and 3D CNNs causes difficulties in deployment. We find that LiDAR point clouds are only reflected on the nearing surface of objects. We name this property as Hollow-3D property. This property makes it possible to first project the points into different views and then hallucinate the 3D representation by combing multi-view features. Besides, the projected points in the perspective view and the bird-eye view are well complementary to each other. Please see the figure B on the slide. The projected points are densely distributed in the perspective view, which looks similar to the RGB image in figure A. Obviously, the features from the perspective view are rich in semantic context. However, the objects are heavily occluded by each other, make it difficult to localize them. The figure C shows the visualization of the bird-eye view. On the contrary, projected points in the bird-eye view are extremely sparse, making it difficult to distinguish the semantic components. But, in this view, the size of objects are consistent regardless of their distance to the ego sensor, and the objects are not likely to overlap with each other. Thus, features extracted from the bird-eye view are applicable to predict the scales and locations of objects. By consolidating the mentioned properties, we propose the hallucinated Hollow-3D RCNN for 3D object detection. The workflow of our method goes like this. Given the input point clouds, we sequentially project the points into the perspective view and the bird-eye view for feature extraction. The point-wise features projected into the bird-eye view not only comes from the raw points, but also includes the perspective view features. We share the features between bird-eye view feature extraction and the region proposal network, so that the cost of RPN is negligible. After obtaining the multi-view 2D features of each points, the Hollow-3D features are generated by bilaterally guided multi-view fusion and a following voxelization operation. At the end, the box refinement module capitalizes on hierarchical voxel RoI pooling to extract proposal features from the Hollow-3D voxels, and makes further box refinement in the detect head. In below, we list several key points for our methods. And we will elaborate these designs in the following slides. To project points into the perspective view, we need to convert the coordinates of points from Cartesian coordinates to cylindrical coordinates. In the perspective view, the points are projected to the cylindrical surface. And in the bird-eye view, the points are proected to the xy plane. Note that there are two groups of indices here. One is projected indices and the other is grid indices. The projected indices are computed by minusing the low range and divided by the grid size. The grid indices is obtained by rounding the projected indices down. We use the unique scatter voxelization to perform points projection. We first find the unique grid indices. And then we take the scatter max operation to perform max pooling over the points in each grid. Compared to the projection methods proposed in point pillars, we don't need to drop points during projection. Besides, this operation enables gradient backpropagation from the projected grids to each points. After extracting the features in the projected view, we exploit bilinear interpolation to regenerate point-wise features. In this time, we use the projected indices instead of the grid indices. The point-wise features from the perspective view and the bird-eye view are then combined to hallucinate the 3D representation. Here we devise the BGMVF block to fuse the multi-view features. It is presented in the left side of this slides. Although there are some simple operators like element-wise summation and concatenation, adopting these simple operations will inevitably ignore the differences between these two views, incurring hard optimization and suboptimal performance. On the contrary, BGMVF introduces the information of one view to guide underlining the complementary information of the other view, effectively boost the combined feature representation. After multi-view feature fusion, we voxelize the points again to get the H3D voxels. The voxelization targets to avoid the bad effects of anormal points, and enable the application of voxel RoI pooling. Once we get the H3D voxels and the region proposals, we can extract features of each proposal for further box refinement. Here, we propose a hierarchical version to further accelerate voxel RoI pooling. In voxel RoI pooling, the computational cost of grouping neighbor voxels grows cubically with the partition grid number and the query range. It means that if both the grid number and query range are large, the computation cost cannot be neglected. In HV RoI pooling, we divide the proposals into grids with two different resolutions. The fine resolution are equipped with small query range, while the coarse one are equipped with larger query range. After performing local feature aggregation, features of the coarse grids are upsampled to the same resolution as the fine grids. Then, they are combined to get the RoI features. After extract RoI features, the region proposals are refined by the detect head. The detect head of our H2 3D RCNN is the same as PV RCNN and voxel RCNN. We compare our method with other algorithms on the widely adopted KITTI dataset, and the more challenging Waymo open dataset. This table shows the performance comparison on the KITTI test set. Our H2 3D RCNN achieves the best performance on the most important car class. And our performance on pedestrian and cyclist slightly trails some strong competitors. This is mainly because the scale of pedestrians and cyclists are much smaller than cars. When these two kinds of objects are distant to the ego sensor, there are only few points reflected by them. Although the projected points in the perspective view are densely distributed, few points cannot provide strong semantic evidence for detecting these objects. To address this issue, a potential solution is to involve the RGB images to ameliorate the detection precision of pedestrians and cyclists. We also report our method with other methods on the KITTI valset, and elaborate the runtime comparison. In this table, we can find that our method achieves state-of-the-art performance on both moderate and hard levels for car detection. And the runtime of our methods achieves 37.1 FPS on RTX 2080 Ti-GPU. This runtime approaches to point pillars, which is famous for its high efficiency. Let's see another two tables that report the performance on Waymo open dataset. Our H2 3D RCNN also exhibits great potential on this dataset. Despite also with multi-view features, our methods outperforms MVF and pillar OD by a large margin. And our method shows the leading performance for detecting in different ranges. We showcase the visualization results of several scenes from the KITTI dataset. Our method can precisely detect the objects even on the challenging crossroad or in a single scene with more than 17 cars. These qualitative examples further provide intuitive evidence on the effectiveness of our approach. That's all for the presentation. Thanks for your listening. Please feel free to try our method with the provided repository.